All right, our next speaker is Sunil Simha from UC Santa Cruz, and he's going to be talking about the cosmic web.
Okay, hi everyone. My name is Sunil Simha. I'm a graduate student at UC Santa Cruz. And today I'm going to talk about some of the work that our group is doing on the FLIMFLAM survey, and our aim is to map the cosmic web, get some constraints on the ionization and such things. So, okay, that works. All right, so here are some of my collaborators who are working on this project. So I'd like to give them a shout out. Thank you, everyone. And so without further ado, let's begin. To give you some context about the project that we're working on, we need to go into prehistoric times to -20 BC, that is before COVID, when astronomers had to worry less about getting infected and more about stuff that was missing. And in this case, it was the matter that was missing in the universe. So baryon census surveys were done, and people found at low redshifts gas in galaxies and absorbers and some tracers of hot gas, but they were not able to account for a sizable chunk of the matter in the universe. And this matter was expected to be part of the warm-hot intergalactic medium, which is extremely diffuse gas, and it's present in the cosmic web filament, and so it's really hard to detect it. Simultaneously, a new class of transients were discovered just last decade. It was called fast radio bursts. This was the first one was discovered in 2007 while looking through archival data, and so this is the famous Lorimer burst. And so what FRBs are essentially radio transients that last for millisecond durations. Yeah, as far as we know, we have not detected any optical counterparts for this. So this is a strictly radio, maybe X-ray phenomena with a star about that. And basically what this is so an FRB is a pulse-like emission, and this emission passes through a whole bunch of material between us before reaching us. And so namely the host galaxy ISM, the host halo, the cosmic web, and the Milky Way and ISM and halo. So as it passes through this stuff, the light gets dispersed. And this dispersion is seen as a delay in the arrival time of the pulse at different frequencies. So the higher frequencies arrive first, and then they're followed by lower frequencies. And this dispersion measure, or DM, not to be confused with the formal mirror, is the sum of the dispersion measure contribution from each of these individual constituents of or reservoirs of electrons. So you have the host, the contribution, the cosmic web contribution, and the Milky Way. And so as people started localizing FRBs, that is pinpointing their exact locations in the sky so that we were able to associate a galaxy with them and hence get their redshift, they were able to start estimating the cosmic web contributions to the FRB dispersion measures. And when you plot the cosmic DM versus the redshift of the FRB, you get this wonderful coincidence with the theoretical expectation from a lambda CDM universe, that is, the FRBs do indeed trace the expected curve for the dispersion measure relation. And this is called the McCart relation in honor of J.P. McCart. So basically, this showed that FRBs actually prove the existence of this missing matter. It's there, but it's just invisible. And so we can totally detect the missing matter. But the question now is, where exactly is it? The dispersion measure just tells us that it's there, but we have to do a little more work to find out where it is. And so that's why we did this end-to-end study of a particular FRB sightline, FRB 190608, and that end-to-end study essentially involved trying to account for the dispersion measure contributions from each of the individual foreground components. So starting with the Milky Way, ISM, and then using SDSS and KCWI data, so basically redshifts of galaxies to model the cosmic web filament and the overdensities to get the dispersion measure contribution from here. And then using KCWI observations of the host galaxy itself to estimate, again, the dispersion measure from the host galaxy. So it was a comprehensive study, and we were, in the end, right. So this is the, some of the observations that we took with KCWI to try to constrain the dispersion measure from the individual intervening halos within a 1 arc minute by 1 arc minute field of view. Similarly, we used like redshifts from SDSS for a large scale reconstruction of the cosmic web density. And so in the end, we were able to show that roughly about a fourth comes from the DM comes from the Milky Way, about a third from the host itself, about 5 to 8% from the halo gas of intervening galaxies, and about a third again from the diffuse IgM. So a foreground mapping can indeed determine where the missing baryons are. So this is a wonderful proof of concept, and we were able to show that such a study can indeed prove to be powerful. However, in the study, there were some model parameters that were uncertain, and we had to just assume some values for it, starting with the FIGM, the fraction of baryonic matter in the cosmic web filaments. Remember, this is basically the missing matter. And so we didn't have direct observational evidence for what this number exactly should be. The F hot, the fraction of CGM gas in the hot phase, so basically whatever stuff in the halo is contributing to the dispersion measure, the typical radial extent of the halo gas, and the host galaxy dispersion measure itself that proves to be a challenging thing to determine for multiple FRBs. And so what one would need essentially are multiple FRB sightlines to try to start constraining some of these model parameters. And so in this work led by my collaborator, KG Lee, that came out recently in arXiv, they showed that with about 30 or so FRB sightlines with the foreground mapping that we're doing, we can start indeed laying about 10% constraints on some of these individual parameters. And key to getting these results are large-scale redshift surveys done with the AA omega spectrograph on the AAT, and LRIS-DEMOS KCWI observations for the halo contributions themselves. Of course, like if we didn't get this large scale data, then the constraints would be much looser, even with a higher number of FRBs sightlines. And so this is how the FLIMFLAM survey was born. This is the FRB line of sight ionization measurement from light cone A omega mapping. And so it's a mouthful, but the acronym is nice. So essentially, Lee et al. Showed that by reconstructing some mock FRB sightlines with mock foreground redshifts, they were able to start getting estimates of how many FRB sightlines are necessary, and that's what the Fisher plot was from the previous slide, to start constraining F hot, FIGM, and so on and so forth. So the goal at the moment, in the immediate future, is to try to get this sort of redshift measurement for multiple FRB sightlines using the A omega and the Keck instruments, try to constrain the FIGM and F hot to roughly 7% accuracy. And so the density field reconstructions happen with a software called Argo. So the input are essentially the halo masses of the individual galaxies and their redshifts. So, and this is, and the algorithm spits out a cosmic web density based on a Bayesian framework. And so using this, we can start estimating what the FRB dispersion measure from the IGM is. And so I'll end this my presentation by talking about what the current status of the project is. It's pretty much ongoing. At the moment, we have already obtained quite a few observations of a number of flight lines. So we have, for instance, so this is FRB 180924. We have gotten measurements of redshifts for many of the foreground galaxies. And we have also gotten DMOS observations of a few sightlines. So we have some redshift estimations. And going into the future, we will start getting results after processing some of this data. So thanks for your patience, and I'm open to questions now. Yes. Okay, so the question is, have we tried folding in the model parameters into the Fisher matrix forecast? So yes, that's essentially what the forecasts are about. So the forecasts are giving us estimates of, so they basically tell us, so we allow the model parameters to be uncertain, to be varied, and then we get a number, how many number of sightlines we need from the Fisher matrix to get a certain accuracy for the model parameters. Oh. Oh, that's okay. So sorry, the question was whether what the expected distributions of the model parameters are. This is a good question, and I'm unfortunately not entirely qualified to answer this. I can, of course, forward this question to my collaborators who actually ran these simulations and get back to you about it.
I have a question.
Yes.
It's maybe not a question, but some FRBs are repeating. Have you ever looked at the same FRB and tried to redo your analysis?
Oh, that's a good question. Yes, sorry. So the question was, some FRBs repeat. Have we tried to redo our analysis with any of these repeating FRBs? So the answer is no. So the repeating population is mostly coming from the Chime catalog, which is there in the north, and its localization ellipses are, well, pretty large, and we can't really get this sort of precise redshift information for the FRB itself. The southern repeaters are few, and yeah, we haven't really gotten large scale redshift information for those fields yet.
Are there other questions? All right, let's thank Sunil and all the speakers for this session.